When we look at satellite motion or orbital motion, there's a few things that we need to think about. And let's first remember that we've got a force from gravity. Now, if we have an Earth, if we have an Earth like that, and we've got an object sitting up there, it's going to be attracted to the planet. And what's going to happen? It's going to be attracted and it's going to accelerate down to the planet and smash O. Right? So why don't satellites fall down? This is the issue. Now the whole point is, if we can give them a big enough vertical velocity, tangential velocity, that is at right angles to a point connected from the object to the center of the Earth, then the force of gravity, that one, is going to act as a centripetal force. And so if the velocity is a velocity that totally needs every bit of that gravitational force to go in a circle, then there's going to be no force left to pull the object even a teeny weeny little bit closer to the Earth. So the weight force at that radius, and the force at that radius, remember, is equal to gmm over r squared. Now, that's not the same force as on the center of the Earth, because look what happens. As the radius gets bigger, the force drops off quite quickly, because it's not just getting bigger, it's being squared and getting bigger, or getting bigger and being squared. So the force drops off very rapidly. So that's the force that's operating on this object, which we'll call a satellite. And so if we want that force to be totally used up, then we could say that that force is equal to the centripetal force. Right? Totally used up. That's the cool thing. So if you make this go fast enough, it will go round and round in what we call an orbit. It's very cool. And so let's just have a look here. Which m's are we talking about? Well, the m of the satellite, because the big M is the m of the Earth. So we can now figure out a formula for the velocity. We can cancel out the r on each side, and we end up with the velocity is equal to big G, big M, mass of the Earth, all over r, square root. That's our formula for the velocity of a satellite. Now, as usual, remember when we do this, you could write this like that. Big G, big M, all over square root r. Get used to working with your square root signs. You often have to change formulas around in maths and physics and science and stuff. So what we're basically saying, though, is this relationship is inversely proportional to the square root of r. So as r gets bigger, the velocity gets smaller. So as our satellites go out further, the velocity they need to go round is slower. So you'll find that the velocity of the ones that travel very close to the Earth, spy satellites, are very fast, and they will do an orbit in about 90 minutes. And normally what you do is you don't do them round the equator, which you could. You do them round the pole. But that way, the satellite's going round, if we're looking down on the pole, satellite's going round this way as the Earth rotates that way. So since it goes round every 90 minutes, then through the course of a day, it's going to go over different parts of the world. So in the course of about a day, it's going to see every bit of the world, which is great. What else can we figure out about this? We could figure out the period. Obviously, if you know the period, well, if you know the velocity, you can figure out the period. Remember, the radius we're talking about here too is from the center of the Earth to where the satellite is. So don't think it's just from the surface of the Earth. And remembering that the radius of the Earth is about 6.37 times 10 to the 6 meters. So if I then want to go another 100 kilometers, I would add that onto there to do all this. Don't forget that little point. So if we want the period, we have to go t equals distance, 2 pi r, all over velocity, right? Or velocity equals 2 pi r over distance over time. So the time is equal to distance over velocity. But we just figured out a velocity, right? And we figured out that it was square root of gm over square root of r. So 2 pi r all divided by square root of gm, big G, big M, and we can put the square root of r back up here. What's r times the square root of r? How do we write that? So what I like to do is to keep everything as seemly as possible, so we can just write this one as 2 pi r to the, well, it's 2 over 2 plus 1 over 2, that's 3 over 2, right? All over the square root of gm. And that's your formula for the period. So if you were given a question where you know the radius and they want to know the period, that's the formula. If you are given a radius and you want its velocity, that's its velocity. Now we have what are called geostationary satellites. Geostationary satellites. Now these guys circle the equator, and what you can do is there's a certain radius. We just figured out our time is equal to 2 pi r to the 3 over 2 all over square root of gm, right? That was our formula for period. Sorry, getting a bit all around the place. What we can do is we can go out to a point where the period is equal to 1 day, or 24 times 3,600 seconds, right? At that point, the satellite's going to stay in the same place. You could also figure out its radius at that point, right? Once you've got its period, if I plug in the period, I can figure out its radius, but it will stay in the same place. This is what Optus, whatever it does, Optus D3, or whatever that satellite is that we get our free to view in our sky with, does. So those geostationary ones, they stay in the same place all the time. They're moving very fast. Not that fast though, because remember we figured out that V is equal to the square root of gm over r. But they're moving fast. They're moving at the same rate as the point above the Earth. Now the thing is this, okay? The whole thing about the equator is important, because different parts of the Earth, if this was, so that's kind of like the equator there, that bit goes round at whatever it is, 460 meters per second or something like that. If that's going round very fast, what about up here at latitude plus 30 or minus 30 or latitude plus 90? This one's not spinning round at all, okay? So that part of the Earth is not spinning round at all. So if you're going round an orbit, polar orbit, you're not going to stay in the same position, all right? And you can't have a satellite just going around that bit. The satellite orbits the center of the Earth, all right? So if you had it off center a little bit, you're not going to get a geostationary satellite, so it's got to go around the equator. All right,